In this video, I'm going to prove the Taylor expansion with the Lagrange remainder and Cauchy remainder. So if we are given the function is differentiable all the way up to n plus 1th order derivative over open interval AB, and so we can conclude that there exists a Cauchy inside open interval x naught x. Usually x is known to be a variable, it's changing, but right now, for now, let's just hold it fixed. Right? Hold both x naught and x fixed, right? Just without any restriction, no specialty, right? Then, of course, x naught and x are within the open interval AB. Then we can write down fx as the sum from 0 to n of the kth order derivative of x naught over k factorial times x minus x naught to the power of k plus Rn of x, right, equal to Lagrange remainder or Cauchy remainder, both true. And of course, these two Cauchys may be different, probably different. First, we're going to prove this lemma. Then we're going to use this lemma to prove our desired result. So, to prove this lemma, right, to prove this equation under these conditions, first of all, we can write down equivalent expression. That is to move this expression over to the left-hand side, right? All we have to do is we just have to prove that there exists a Cauchy, so that f prime of Cauchy minus lambda prime of Cauchy times f of x naught minus f of x is equal to 0, right? So the Cauchy is within the open interval x naught x. Without loss of generality, we can just assume that x naught is less than x, right? So that we can write down this open interval. And let me just write down fix both x naught and x, and of course under these conditions. So the reason is because we're motivated by the derivative, right? Then we can find its antiderivative, right? We can construct a new function called h of t. That is f of t, right? That is its antiderivative, minus lambda of t times quantity f of x naught minus f of x. This is just a constant, because remember we hold both x naught and x fixed, right? So simply we can just verify h of x naught. Right, that is f of x naught minus lambda of x naught times f of x naught minus f of x, right? So, of course, we assume these conditions are satisfied, right? So we assume lambda of x naught is equal to 1. So lambda of x naught is equal to 1. So we have f of x naught minus f of x naught, 0. Minus minus plus f of x. Let's verify h of x. That is equal to f of x minus lambda of x times whatever. So we assume lambda of x is equal to 0, right? So this is equal to f of x. So in other words, h of x naught is equal to h of x, and also h of t. Is it continuous? Right? Is it continuous over the, what is h of it? Yes. Like I said, h of x is just, all right, the f of t minus lambda of t. f and lambda are assumed to be continuous. And of course, h is continuous as well. And because f and lambda are assumed to be differentiable in this open interval, so therefore h of t is also differentiable in this open interval. Therefore, and also because h, the function, is equal to each other at both edges, so therefore, according to the Rolle's theorem, we can easily conclude that there exists some Cauchy inside the open interval x naught x, so that the derivative of h of Cauchy is equal to exactly 0. Right? What is h prime of Cauchy? H prime of Cauchy, right, is f prime of Cauchy minus lambda prime of Cauchy times this, right? Equal to 0. Equal to 0. So meaning this equation is true, right? So this is proven. So let me just denote, let me just use t sub n of f x naught x to represent the sum from 0 all the way up to n of kth order derivative of x naught over k factorial times x minus x naught to the power of k, right? This part, right, this is called the Taylor polynomial of degree n, right, because it has something to do with the leading degree, right, that is n, also has something to do with the function f, has something to do with the points x naught and x, right? That's why we denote it in this way. So next job for me is to construct an appropriate lambda of t. Right? How can we, and also, of course, also construct an appropriate capital F. Right? That's the most difficult part. So let me just say, my capital F of t, the way I want to construct it is simply replacing x naught with t. This is my capital F. I'll explain why. But I don't know the motivation, right? But it's just, so f that is equal to first term. What is that? First term, zeroth order derivative is a function itself, right? X naught replaced with t, just f of t. What's the second one? Second term, right? First order derivative, f prime of t over 1 factorial times x minus t to the power of 1. What's next term? That is half, right? 2 factorial, f double prime of t, x minus t to the power of 2. Next, so on and so forth, all the way up to n factorial, the nth order derivative at t times x minus t to the power of n, right? And let's find out its derivative. So f prime of t. Right, so the reason we replace x naught with t instead of replacing x with t is just so that when we calculate its derivative, we can successfully cancel out the majority of the terms. Here's why. So the first one is f prime of t. Then we have a product of two functions. What do? We differentiate first. F double prime of t. Copy it times the second. Then what do? Copy down the first. Differentiate the second. Differentiate. There's a minus sign coming out. chain rule. Just multiply by 1. Right, t. Yes. So this one, likewise, we differentiate the first one. Right. 2 factorial f third order of t times the second one. Likewise, there's a minus sign coming out, right? Following the chain rule. Copy down the first one. 2 factorial f double prime, right, times 2 times x minus t. Right, minus sign because the chain rule, minus sign coming out. So in the end, we have so on and so forth. Right, the last one, likewise, differentiate the first one, n factorial, and n plus 1 order at t, right? Copy down the second one. Likewise, there's minus sign coming out. Copy down the first one. Differentiate the second one times n x minus t to the power of n minus 1. So what's the pattern here? We can perhaps cancel out the majority of the terms, right? F prime of t minus prime of t, right? And also this one, right? 2 and 2 cancel out. F double prime times x minus t. Right, this and f double prime times x minus t, they just cancel out. Right. Right, so the pattern seems like if we just end with this pair, then we're only left with the first one of this pair, right? Second one is gone. But we're ending with this pair, so meaning we only keep the first one. The second guy is gone. All right, that's the pattern. So likewise, this guy will be gone because it'll be canceled out with the second guy of the next pair, right? Somewhere there. Right? We're only left with this term. Right, that is my f prime of t. Right, let's find out what's the value of f of x naught. Right, what is that? That is f of x naught plus f. Right, that is nothing but t n fx naught x, right? Because remember, I constructed f of t using replacing x naught with t, right? This is mine. So therefore, if I still use x naught, right, it should still be the same thing, the very thing, right? That very thing. T n f x naught x, right? Then what's my f of x? Replace t with x, right? X minus x, this one's gone. X minus x, this one's gone, right? Every term is gone except for the first term, right? I still have f of t. Right? F of x, right? T replaced with x. Right, so I want to work out that difference. The difference is Tn f x naught x minus f of x. Right. So I'm getting very close to this format. So now I've just constructed a function in terms of t. Right. That is Tn f tx. That is simply replacing x naught with t. All right, so denoted as this, just to save some space. And so worked out the derivative of f. Turns out to be this simple function. So since I've cancelled out every term right, previously, so that's the benefit of constructing such function, right? So that we can cancel out every term except for this term. And so if we replace x with t, then we wouldn't have such effect, right? May not work. So also f of x naught is given by this, right? And replacing still the same thing, right? Same thing. F of x turns out to be little f of x. Simply we just replace t with x, right? Replace x naught with x, right? Therefore, only the first term remains. Every term is cancelled out. So what's my lambda of t? I want to construct lambda of t. Right, such lambda that satisfies these conditions. So it has to be x minus x naught, x minus t, quantity to the power of n plus 1. Right. So the motivation of constructing such a function is because we've compared the desired result, Lagrange remainder, right, and our Taylor expansion, and with our lemma equation. Right? I'm not going to go into details, but that's easily can be thought of. So that is the lambda of derivative that is equal to x minus x naught to the power of n plus 1. And we have minus n plus 1 times x minus t to the power of n. Right now, just treat x as a constant. Right, according to the chain rule, the minus sign coming out. And also, let's verify what's lambda of x naught. Right, x minus x naught, right, over x minus x naught. Turns out to be 1. What's lambda of x? Right, x minus x turns out to be 0. Right, is lambda continuous? Continuous over this closed interval? Yeah. Yes, of course. Is it differentiable? Yes. So lambda really satisfies our conditions. Right, so therefore, so our f of t also satisfies our conditions, right? So therefore, according to our lemma, we have the left-hand side f prime of Cauchy. And there must be some Cauchy inside open interval, so that f prime of Cauchy, that is f n plus 1 of Cauchy over n factorial times x minus Cauchy to the power of n is equal to lambda prime of Cauchy. Just replacing t with Cauchy. Just minus x minus x naught to the power of n plus 1 times n plus 1 times x minus t Cauchy to the power of n times fx naught minus fx, right? That is this minus that. Tn f x naught x minus f of x. All right, then we can isolate this. Tn f x naught x minus f of x is equal to, I can cancel out this x minus Cauchy to the power of n, right? X minus Cauchy to the power of n, they just cancel out, right? Divide this over. I have minus n plus 1, n factorial. We have n plus 1 factorial. At the bottom, we have f n plus 1 of Cauchy. And we have x minus x naught to the power of n plus 1. Right? Then we simply work out f of x equal to Tn of f x naught x plus this, right? That is Rn of x, right? Right, this is Rn plus of this. What is this? Lagrange remainder. Exactly, Lagrange remainder, right? So now I want to construct a lambda of t, right, for Cauchy remainder, a different lambda of t, right? For the same motivation, right, as I construct for Lagrange remainder. This time it's a little different. The x minus x naught, x minus t. All right, let's just verify lambda of t if it satisfies conditions. All right, so lambda prime of t. Right, what is this? We have minus 1 over x minus x naught, right, treating x as a constant. And let's verify lambda of x naught. Right, x minus x naught, x minus x naught, right, turns out to be 1. Verify lambda of x, right, x minus x, 0, right. Right, lambda, is it continuous? Right, of course, continuous. Right, is it differentiable? Yes. And of course, f also satisfies the conditions. So therefore, we can just simply apply our lemma. Right? So there has to exist some Cauchy. Maybe different Cauchy than previous for Lagrange remainder. Right? Cauchy that's in the open interval. Right? So that f prime of Cauchy. Still this t replaced with Cauchy. F n plus 1 of Cauchy over n factorial times x minus Cauchy to the power of n, and that is equal to lambda prime of Cauchy. Right? Still the same thing. Right? There's no more t's in here. So minus 1 over x minus x naught times f x naught times f of x, right? Still the same thing. So still t sub n of f x naught x minus f of x. I still isolate this. Right? T n f x naught x minus f of x. That is equal to minus sign, that's what we have, n factorial f n plus 1 of Cauchy times x minus Cauchy to the power of n times this times over to the other side, x minus x naught. Right? Work out f of x. That is equal to Tn f x naught x, and this is removed to the other side, right? Plus this value, right? Rnx. Right? This time our remainder is exactly Cauchy remainder. But in fact, the Taylor expansion with the Lagrange remainder, in fact, can be proven by using the Cauchy intermediate value theorem. And likewise, the Taylor expansion with the Cauchy remainder can in fact be proven by using the Lagrange mean value theorem. It's like inverse use, which will be probably more natural compared with using the lambda function lemma. It may not be that natural. But I think what it does is that maybe it unifies the both the Cauchy remainder and the Lagrange remainder, and also unifies the Lagrange mean value theorem and Cauchy mean value theorem. Maybe that's what it does. But in the future, I will use maybe a more natural way, maybe using just only Rolle's mean value theorem to prove all the theorems, including Taylor expansion with Lagrange mean value, Lagrange remainder, Cauchy remainder, and also including Lagrange mean value theorem and Cauchy mean value theorem, just by using one theorem, that is Rolle's mean value theorem. And last but not least, remember at the beginning I held x naught and x fixed, right? Then proved Lagrange Taylor expansion with Lagrange remainder and Cauchy remainder are both true for any value of fixed x naught and x inside open interval. So now the question is that, is it still true for any value of x, right, and hold x naught fixed inside AB? Of course, still true, right? Because when I held x fixed, there was no restriction. There was nothing special with the value of x, right? Any arbitrary random value of x is fixed. Right? That's why.